All right, is it working now?
Yeah.
Okay. Okay, well, this is so typical technology. It always lets you down when it has a chance. So, all right, anyway, so we'll wait a second for everyone else to come back in. So, I mean, this is one of those times when it was really helpful that everything was being typed down, but still, I just want to go back and revisit what we were doing because, of course, the sound decided to crap out on us. So, let's just wait another minute because I can see not everybody's here. And then we'll just go back and revisit what we just did. It won't take as long because we've already finished it, but I just want to make sure everybody understands what we've been doing. So, all right, let's see. One or two more. All right, so anyway, let's get started again. So again, let's just go back right to the beginning, chapter or question number 5. A card is chosen from a deck. The card is replaced, and then a second card is chosen. So what that means is that we're sampling with replacement, which means that the draws are independent of each other. They do not influence each other because when we pick the second card, the entire deck is still intact. In other words, nothing is missing. And so what that guarantees is that any events that are defined on the first and the second draws are going to be independent of each other. So here we define the event A to be the first card is a king, and B is the event that the second card is black. Okay, now, just as a quick review, in case you're not familiar with the deck of cards, there are 52 cards in a standard deck, half are red and half are black, 26 of each, and each each rank, like kings, queens, jacks, etc., there are 4 of each, 2 of which are red and 2 of which are black. So with that information in hand, we should have no difficulty calculating the answers to these questions. For example, the probability of A, the event that the first card is a king. Now, in a case like this, it would be very impractical to try to write out the entire sample space for this problem because that would include 52 cards. So we're not going to do that, but we do know that there are 52 cards in the deck, each of which is equally likely to be chosen. So that's good enough. And in addition, we probably don't need to bother writing out all the elements in set A or B either, just because there would be a large number of them. And to make things even more complicated, they're not numbers, they're letters. For example, King of Spades, I guess you would write that as KS. So we're not going to write out the elements in these sets, but we do understand how many elements are in each one, and that's really the bottom line. So for the probability of A, we know that there are 4 kings in the entire deck. We know that there are 52 cards, and therefore the probability of A must be 4 out of 52, which can reduce or be reduced to 1 out of 13. And again, the key to the whole thing here really is that the cards are all equally likely to be chosen. If not, then this would be much more complicated than it is. All right, but that makes things a little bit simpler. So for B, we know the probability of B that the second card is black is 26 out of 52 because we know that there are 26 black cards in the deck and there are 52 cards in the entire deck. Okay, and so if you want to, you can simplify that to 1/2 or 0.5. All of these are fine. All right, now A complement. For this one, we want to calculate A complement using our rule. Although if you wanted to, you could define the set A complement as simply being all the cards that are not kings. But it's probably quicker and easier to do it this way. It turns out that 48 cards in the deck are not kings because 4 of them are. Therefore, this probability is 48 out of 52, which reduces to 12 out of 13. And again, this part is not absolutely necessary. For the same reasoning, B complement would therefore have a probability of 1 minus the probability of B, or 1 minus 26/52, which reduces to 1/2 or 0.5. All right, now this is the first tricky one, the probability of A and B. In other words, the probability of getting a king on the first draw and a black card on the second draw. Since we've already seen that A and B are independent of each other, we can therefore use the simplified multiplication rule here. Okay, once that's established. All right, that's better. Yeah, so that means that we can use the simplified multiplication rule, which means we can basically just multiply the probability of A times the probability of B to come up with our result. Now, we already know these two probabilities, so we just plug them in, and we end up with 1 out of 26. And it's just that simple. And again, it's because of the independence of these events that we can do this. Otherwise, it would be a lot more complicated. Now, for the conditional probabilities, we just simply use the definition of a conditional probability, which means we have the joint probability of A and B in the numerator. The probability of B goes into the denominator. And these numbers we've already calculated. So we'll just take the ratio of 1/26 over 1/2, and that leaves us with 1/13. Okay, and so similarly for B given A, the numerator is the same. It's the probability of both A and B being true. In the denominator, we have the probability of A, okay? So now we've got the ratio of 1/26 over 1/13, and that's equal to 1/2. So, and when you think about it logically, what they're telling you here is that, well, we don't really need to think about it that way. Just all we do need to do is use the rules. But anyway, are A and B mutually exclusive, and why or why not? And don't forget about this part. You're supposed to explain in these cases why or why not. Okay, now the answer is no in this case. And there's a few different ways, as we've seen, of expressing this. But here, the quickest and easiest way is simply to point out that the probability of A and B, or the intersection between them, is not empty. In other words, this probability is not zero. In other words, another way to think about it is that it's possible for both of these things to be true, and therefore they're not mutually exclusive. Okay. All right, independence. Now here we've got two approaches we could take. We could take the traditional approach and show that both of these conditions are true. And remember, we have already calculated all of these probabilities. So when you compare them side by side, you can see that the first condition is true and the second condition is true, which means that A and B are independent. The other option you have is to simply point out that, you know what, these cards were chosen with replacement, which means that A and B must be independent because they refer to what happens on the first two draws. All right, so here's the English version. Here's the math version. Okay, so either one works in this case. And then the complements, in order for A and B to be complements, we know that two things have to be true. And we can show very quickly and easily that the first one is false. We know already that these two events are not mutually exclusive. Therefore, we don't have to bother checking the second condition. And that means that we have our answer. A and B are not complements. All right, so this is where we're able to go. Now, here we have in question 6 another set of probabilities, but this case is very different because we do not know what the experiment was that generated these outcomes, which means that the only way we can solve these problems is to use the rules. Okay, there's really, in these cases, there's really only one way to go because you don't have enough information to tell, like to explain this in English, for example. So for these cases, when you only have probabilities without any knowledge of the underlying experiment, then your best bet is typically to use just the rules. So for example, here, the probability of A complement, we know, is equal to the 1 minus the probability of A. So since A is 0.2, this is 0.8, okay? B complement, same thing. The probability of B complement is very easily calculated as 1 minus the probability of B, which is given up above as 0.5, and that just leaves us with 0.5. Very good. All right, now the addition rule. Now in this case, we're going to use the full addition rule because you can see that A and B are not mutually exclusive. Okay, so the full addition rule means that we take probability of A plus the probability of B minus the intersection, which equals 0.2 plus 0.5 minus 0.2, which reduces to 0.5. Okay, so yes, we're using the full version of the addition rule because the two events are not mutually exclusive. All right, so the conditional probability, we've already seen, this is simply equal to the ratio of the intersection between these two. Okay. In this case, we're dividing by the probability of B, which is 0.2 divided by 0.5, which is 0.4. All right, now how about B given A? Let me steal this for a second. So with this formula, remember the only thing that changes is the denominator. The numerator is still the probability of A and B. The denominator now becomes the probability of A because that's the information that we have. So the numerator stays at 0.2, but the denominator is now 0.2 because that's the probability of A. And so this one gives us an interesting result. It's 1. What this is saying is that if A is true, then B must be true. Very interesting. Okay, now, are they mutually exclusive? Why or why not? Well, let's see. No, because you can see that the intersection, this probability is not 0. Oh, whoops. Okay. Let's see, where are we? Okay. We need that unequal sign. And that's all you need to know. They're not mutually exclusive because the probability of A and B is not 0. Now, are A and B independent? Okay, this requires us to show that, as we've seen before, two things are true. The probability of A given B must be equal to the probability of A, and the probability of B given A is the probability of B. Well, let's find out if that's true or not. This first one, the probability of A given B, we've already proven, is 0.4, and the probability of A, we were told in the beginning, it's 0.2. So since these are not equal to each other, we know that A and B are not independent. Okay, so in other words, both conditions must be true for this to have independence. The first one is false. Therefore, we're done. A and B are simply not independent. How about complements? All right, now remember, this requires us to show okay, so this is the one where the union has to equal 1. And you can see already it doesn't, but let's just carry on with this. And that the probability of the intersection must be 0. So the probability of A union B we showed earlier is equal to 0.5. Since this does not equal 1, we know that A and B are not complements. Okay, already the first condition is false. Therefore, we just stop and we conclude that A and B are not complements. Okay. All right. So is everyone following what we're doing? So the basic questions themselves have been the same for like 3 problems in a row, but the information that you were given was presented a little bit differently. And in fact, the same thing will be true for question 7, because you're basically being asked the same kinds of probabilities, except this time you have this table, the joint probability table, which you did not have for these other problems. So here, things are a little bit easier because a lot of the information is already in the table. Okay, so basically, there's many different, well, I shouldn't say many, there's several different ways that this information could be presented to you, but the basic rules never change. Okay, so why don't we get these, so we're back to Starbucks again. And so for this one, FND simply means decaf French roast. Look how easy that is. And you notice this table, these are already probabilities. When you see the grand total is 1, these are probabilities. These are not the original numbers. As we saw in the slides, when we had that example with the business school and the students, we had the actual numbers. And for each probability, we had to divide by the grand total, which was 500. Here, that's already been done. So these numbers themselves are already probabilities. For some purposes, that makes things a little easier, but for some purposes, that is a bit of a problem. If we wanted to know, for example, the exact number of bags of French decaf that they'd made, then we don't have that information, but we do know the probabilities. So for our purposes in this question, that's all we need to know. So this first one is 18% or 0.18. R&D is regular espresso, which is here, 0.10. RNG is regular Guatemala. Oh, hold on one second. The doorbell just rang. I'll be right back. All right. That's one thing you don't have to deal with in school, doorbells. Anyway, so RNG is regular Guatemala, 0.12 right here. F rather is French roast of all types, whether it's decaf or regular. So that would be right here, 0.46. R is regular, right here. The total of all the regular styles is 0.5. Now for D complement, we can approach this 2 different ways. We can use the complement rule, but we can also note that because of the way this table is set up, all the coffees have to be either decaf or regular. And of course, there's no coffee that's both. And so what that implies is that decaf and regular are complements. So this question, this 1 minus PD, is also guaranteed to equal the probability of R. Okay, but I think it's easier to just use the rule. But I just, want to point out that these 2 are in fact complements. Now here we're using the addition rule. So I want to make it clear again that it's understood that these rows and columns are all mutually exclusive of each other. Okay, so there's no coffee bean that can be both French roast and Guatemala, for example. So that means we can use here the simplified addition rule. And so F by itself is 0.46. G by itself is 0.22. Oops, 0.22. So they add up to 0.68. Okay, it's that simple. All right, now how about GUE? This is either Guatemala or espresso. So we use the simplified addition rule because, again, they are mutually exclusive. 0.22, 0.32, that's good. Now, Here we go. The conditional probabilities. All right. Let me just type that in here. So the calculation hasn't changed. Now, by the way, I just want to remind you that the probability D and F is the same as F and D. Okay, and that's 0.18 because they both mean decaf French roast. So 0.18 over 0.46, okay, which is approximately equal to 0.3913. Okay, now this one is regular given espresso, so we need in the numerator R and E over E. So R and E means regular espresso, 0.10. And E by itself is 0.32. And that's approximately 31. Actually, this one is exactly 3125. Okay, and then we have one more, which means we're going to have the joint probability of G and R, which is Guatemala and regular, over the probability of regular. So G and R is right here. Regular Guatemala is 0.12. Regular is right here, 0.5. And that is equal to 0.24. Okay, so those are done. I guess I'll be consistent and make them all boldface. So these are pretty straightforward. You know, it's just once you get used to the idea that these are joint probabilities, okay, and these are the so-called unconditional probabilities, as well as these two, it all pretty much falls into place. Then it's just a question of following the rules. These are a little more conceptually challenging, but still, I think they're pretty straightforward. All right. So is there anything that you don't get? You want to go over it again? Okay, good. All right, so like the other three, I think I was able to show you before, even when we had no sound, that these are already here. I'll just post this when we're done. Now, by the way, of course, today's Thursday, so we're not going to meet again until Monday. So remember what we're going to do here. What I'd like you to do is have the problem sets from 3 and 5 ready by tonight, midnight, Eastern time, that is. And then what I'll do is I'll post the midterm itself. And I think we already agreed yesterday that because of the holidays and all the rest, and because we're actually making good time with this class, I was a little concerned about that. I mean, there's a lot of material to do over the winter break, but I think we're maintaining a very good pace here. So just quickly look at the January calendar one more time, and we'll see that tomorrow's the 1st. So I think you can have until the 11th to do this first midterm, but that means that the second midterm will be due fairly soon afterwards, like maybe the next Monday. And then that Tuesday is our last class, which means that the exam would have to be due. I'll find out how much time I can give you, but most likely they're going to want, usually they say they want the results within 3 days, which would put it on Friday the 22nd, but it's possible that we can stretch it out to Monday the 25th. I will investigate that. So for now, though, just keep in mind, for tonight, you should have the chapter 3 and 5 problem sets ready. And then for the 11th, you should have the midterm ready. And then in the meantime, we're going to get back into the new material. Most likely we'll do chapter 6 and 7, and maybe even start 8 over the coming week. And that would mean, of course, a couple of new problem sets as well. So, you know, it's a lot, but you know what? We're on break. And I assume that this is the only class you're taking Maybe I'm wrong about that, but you should have plenty of time to take care of this. All right, so let's get back to where we were, which is chapter 6, our discussion about discrete probability distributions. And specifically, we're looking at the concept of the random variable and the probability distribution. Now, so far we looked at the idea of what is a random variable, and we saw that it simply assigns numbers to the outcomes of an experiment. It's really more for convenience than anything else, because it's much easier to deal with numbers than, let's say, letters like E and O. Once that's been done, okay, so here we go. With our die rolling experiment, we assign numbers to these outcomes, which represent the number of even outcomes, or the number of even rolls. You could define it any way you like, but for our purposes, we want to keep thinking in terms of even numbers. For example, let's say you're playing a game in a casino where the amount you win depends on how many evens turn up. So you want to keep track of how often this can happen. And also, of course, the key detail here is the probability of each of these outcomes, which we will see gives us what's called a probability distribution. So the probability distribution is where the outcomes of the experiment are actually assigned probabilities. Now, we also define the moments. These are the summary measures that apply to our discrete random variable. And you can see that they are very similar to what we've already done with samples and populations. The main difference here is that they incorporate probabilities, which we did not have in our previous chapters. Okay, but the concept is the same. The expected value or mean is simply an average. It's a weighted average, specifically where you can think of the probabilities as weights. This is actually a weighted average, just like we saw in chapter 3. Except that instead of frequencies, we have probabilities. You multiply these together, add them up, and you're all set. There's your expected value. The variance is a measure of dispersion, of course. It tells us how spread out the outcomes are from the expected value. We went through that case as well. And just like what we had with the population measures, we're subtracting the expected value from each X. We square the result, multiply by the probability, and add them up. And of course, the standard deviation is simply the square root of the variance. This is, again, something we've seen before. This never changes. No matter what situation we're in, the standard deviation is always the square root of the variance. All right. Now, we were also introduced to we're going to be seeing here two discrete probability distributions that are widely used in different areas like economics and finance and biology and psychology, etc. And the two that we've chosen here are binomial and Poisson. Now, we've already finished our discussion about the binomial distribution. We haven't started Poisson yet. So just quickly, the binomial distribution results when we have an experiment with the following properties. We have a series of trials, like flipping a coin, for example, could be considered a single trial of an experiment in which we flip the coin multiple times. And the key details are these. Each trial must be independent of the other trials, which means they don't affect each other. Each trial has only two possible outcomes, success and failure, we will call them. And by the way, this is where the distribution gets its name from. Bi means two. Now, it's not quite as rigid as it sounds. We can, like, for example, when we're rolling the die twice, obviously each die has 6 outcomes, but if we only focus on evens and odds, suddenly this experiment becomes a binomial experiment. So in other words, we can change the way we define our experiment. And in many cases, we can create a binomial distribution, even if the potential is there for more outcomes. If we define our outcomes properly, then we can, in many cases, take an experiment and convert it into a binomial experiment. So it's a much more general approach than you might think. And then, of course, the last thing we need to observe here is that the probability of success on each trial, which we'll call pi, and by the way, the reason why the book does that is to avoid using p too many times. In other words, if we use p every time a probability is defined, we'll eventually get them all confused with each other. So here they're using the letter pi to represent the probability of success on a single trial in a binomial experiment. Okay, so pi. Don't get it confused with 3.141, et cetera, et cetera. This is meant to represent the probability of success on a single trial. So we're assuming that that probability never changes. Just like, for example, the probability of getting ahead on a coin flip never changes. With all that being said, we can calculate binomial probabilities with this formula, where you recall this piece here actually is a shorthand for the number of combinations that can be created by choosing X objects from N objects. Okay, so this term in parentheses represents combinations. The rest are pretty self-explanatory. The pi is probability of success. 1 minus pi is the probability of failure. And again, which one we choose to be success and failure is completely arbitrary. It doesn't really matter which is which, as long as we're consistent. So remember, this is probability of success. Well, it's actually the probability of X successes, because here's X. And then this 1 minus pi would therefore be the probability of failure. So if we're flipping a coin, for example, if we define a head as success, then tail would be a failure. So this is the probability of a head. This is the probability of a tail. All right. So we went through and explained what combinations mean. And of course, this is the actual formula that we're looking at, where this exclamation point is the factorial operator, which we defined here. Okay. And then we explain what combinations mean. This is these are selections of objects from a larger group where the order is irrelevant. Okay, that's the key detail. With a combination, the order does not make any difference. So we want to know how many ways we can choose X objects from N where the order does not matter. So we use the example of the house painting colors. We had another example with was it toppings on our Haagen-Dazs ice cream. And so once we understand that formula, we can easily calculate any binomial probability that we choose. But I also pointed out that the calculator can do this directly for us with the function binom PDF. Okay, so just remember that. By the way, I did not mention this the other day. If you look at that calculator very carefully, we can use the function binom PDF to solve for, or to calculate binomial probabilities. But the calculator also contains a function called binom CDF. This is only used for what are called cumulative probabilities. So for example, suppose I had the following scenario. Suppose that a coin is flipped 10 times and we define success as a head. Okay, what is the probability of getting, let's say, 5 heads? Okay, so this is going to come from, can be computed with binom PDF. With the inputs, we need X, N, X, and pi. Okay, hold on. Oh, I'm not sure if I can do symbols on. Oh, here it is. Here it is. There it is. Okay. Now, what about this question, though? What is the probability of getting 3 heads or less? Well, this can be calculated as ooh, using Binom PDF and then adding up the results. Ooh, now that sounds like a lot of work, doesn't it? And it is. So what can we do to avoid doing all that extra work? Well, that's when we need Binom CDF. Okay, the other option would be we could use Binom CDF, where n would be 10, x would be 3, and then of course pi would be 1/2, because the 3 represents less than or equal to 3. Instead of the individual values, you would actually have less than or equal to 2 here. In fact, why don't we do this? Just because we could probably use the practice. Let's go back to this. I know it's I don't know. All right, why not? Let's do this. I'm sure everybody could benefit from the practice. Let's do this. Go get the calculators. So we're going to start by calculating this probability by actually doing this. We're going to calculate each individual probability and then add them up. Okay, so for example, we know here that n is 10 because there's 10 flips. Pi is 1/2 because the probability of getting ahead is 1/2. Now for the probability that x equals 0, x equals 0. So you would have Binom CDF, a PDF rather. And if you go to the TI-84, you'll see that it's going to ask you, so you go to second VARS, followed by Binom PDF, and then you would hit enter. And that would give you your Binom PDF. Okay, so let's go do that. Second VARS, Binom PDF, which is, on my calculator, it's A. And then you have to enter. And then what's going to happen is that if you have the 84, it'll ask you for trials, which means n. It'll ask you for p, which is 0.5, and the x value would be 0 in this case, because we're trying to calculate the probability that x equals 0. And you'll plug in your numbers, okay, 10, 0.5, and 0 would give you a probability of it's a tiny one. It's actually written here as 9.7656 e minus 4, which means 9.7656 times 10 to the minus 4 power. Okay, I have to turn that into a superscript, of course. And that means the same thing as all right, it doesn't want to work today. 0.0009766. So that's a tiny little probability. All right. So this is how we get the probability that x equals 0. In this case. Okay, so why don't we do the same thing for 1, 2, and 3, and then add them up and see what we get. All right, so now what's good about this is that each time we do this, you're only changing one thing, x. Okay, so go back to the calculator, change the x to 1. And this time, you're getting a somewhat larger number, 00976, let's say. All right, then let's do the same thing for 2. Okay, 0.0439. Okay. Yes, so we need one more for 3. So change that to a 3 and recalculate it. Point 1172, let's say. Okay, so therefore, the probability that x is less than or equal to 3 is the sum of these 3 probabilities, which equals all right, so let me just copy these in here again, and then we'll add them up. We'll see what we get. All right, that's for 0. This is for 1. Then for 2, we had 0439. Okay. And then we had 0.1172. So let's add those up. Now you can see there's a lot of calculations going on here, and the potential for making mistakes is enormous. Okay, so but let's just add them up. So this is going to be approximately 1718. Okay. Now, suppose we say to ourselves, oh, we don't want to go through all these steps. So we're going to try binom CDF. Remember, now the C stands for cumulative, which helps remind you that this is less than or equal to. Hold on a second. There we go. Okay. So now it's binom CDF. But now X is 3. So now if you look in the calculator, this is actually now, in mine at least, it's letter B instead of A. And so once we choose it, these are the three numbers we would enter, but since we're using CDF, let's see what we get. So 10 trials, 0.5 probability, 3 for X. And it turns out 17, it's almost the same. So it's about 17,188, let's say. So the difference between the two is really the rounding that we did along the way. It is the same number. So in other words, what this does is it gives you the ability for these special cases less than or equal to calculate the number you need very quickly and easily, rather than going through all these steps, which I'm sure you do not want to do if you can avoid it. And that's actually more powerful than it sounds, because let's try this one. Now remember, we flip the coin 10 times. Here's another example of how we can take advantage of this. Suppose we want to know the probability of getting at least one head. Well, that's greater than or equal to 1, which means what you'd have to do if we wanted to calculate this individually with the binom PDF function. That's a lot of calculations. So you might say to yourself, oh my God, binom PDF is a lot of work. Binom CDF doesn't help because that's for less than or equal to probabilities. So what can we do? Well, here's what we can do. We're going to use the following shortcut. We're going to just make a point here that if you add these up, you agree that this has to add up to 1. Of course, because that covers all the possibilities. Now, here's the clever part. These probabilities are collectively what we mean by X is greater than or equal to 1. So what this means is I can write this as this, and then algebraically, oh, what do you know? And 0 we've already seen. It's up here somewhere. Oh my God. So yeah, look at that. 1 minus. Now look how much work I just saved myself. This is equal to 0.999 02344. Now this can be extended very quickly and easily. Watch this one. Example. Suppose instead I said, oh, I don't know, how about, what is the probability of getting at least 4 heads? Well, now what can we do? Oh, I have an idea. let's try this. Now, of course, you can do this yourself. You can do all the individual calculations and add them up. You don't want to do that though, do you? No. So let's think about this for a second. Okay, so what we're seeing here is this. I'm just going to leave some room for what we're going to do. All of this could be thought of as the probability that x is less than or equal to 3. This is the probability that x is greater than or equal to 4. So you can see where this is going now. Wait, let me write it like this. So that implies that what I'm actually looking for is just 1 minus the probability that x is less than or equal to 3, which we just happen to already know the answer to that. Oh, how clever. So 1 minus that is 82. Okay, so in other words, you can actually put this binomial CDF to good use sometimes. It depends on the application, but so the binomial CDF is a useful tool, but you want to be careful with it. You want to make sure that you only use it when you actually have the so-called cumulative probabilities. But having it there saves you from the possibility of having to do a large number of individual probabilities with binomial PDF. So that's why this is so important. And you'll see a lot of this when we're doing the problem set here. And so believe me, it'll help you a lot. It'll save you time. All right. Now, what else did we do in this section? Let's just quickly review these moments. Now, we already know what moments are. We know how they work. We know how they're calculated. We know what they mean. But it turns out that for each particular probability distribution, we typically have shortcut formulas that make it a little quicker and easier to calculate these moments. And the binomial distribution is no exception. For example, look at how easy it is to calculate the expected value. It's just the number of trials times the probability of success. Much easier than the formula we had in the beginning of the chapter, or last chapter rather. The variance. We have, well, actually, no, it was this one, but way back in the beginning, remember we had those really complicated formulas. So I don't know about you, but I'd rather do n times pi than go through all this work. Okay, and similarly for variance and standard deviations, we have for variance n times pi times 1 minus pi. And then finally, for the standard deviation, we have the square root of the variance. Of course we do. That always works that way. Okay, and then we did these actual calculations for the die rolling experiment. And we discovered that the expected number of evens is 1 when we roll the die twice, which makes perfect sense. The variance turned out to be 1/2. And finally, the standard deviation was 0.7071. Okay. And then the last thing we did was we looked at the histograms. We don't really need to go through this again, but just be aware that when the pi is very low, probability of success, it stands to reason that most of the outcomes will be clustered towards the low end here. With pi equals 0.5, we have a nice symmetrical distribution. And when pi equals 0.7, then most of the area is up here. All right, finally, it's time to visit the Poisson distribution. But since it's way past 11 o'clock, I think it's also time for our break. When we get back, we'll introduce the Poisson distribution. And you'll see that, you know, it has a lot of its own useful properties. And as it turns out, of course, the calculator also has a function that will help us calculate Poisson probabilities as well. All right, so let's knock it off for a bit. And then when we get back, we'll look at Poisson. And then, of course, we'll have a long 3-day weekend. Woohoo! That's one of the nice things about the winter session. If we only meet 4 days a week, well, then that means we've got 3-day weekends every week, don't we? Yes. All right, so I'll see you in a few minutes. All right. So it's time to do the Poisson distribution. All right, so Poisson, as I mentioned yesterday, is for a different type of scenario. Instead of a series of trials, what's happening here is that we're observing the passage of time, and we're trying to determine the probability that a certain number of events will occur during that passage of time. So, for example, let's throw in some quick examples here. Just to see how this is different than what we've been doing with the binomial distribution. Let's say, for example, we want to know the number of customers who enter a bank during lunch hour. Could be modeled using the Poisson distribution. Or how about the number of cars that pass through an intersection from, let's say, midnight to 1 a.m. could be modeled using the Poisson distribution. So you get the idea here. It's how many things occur during a specific time frame. Now, it can be used for other things too, but this is the one that we want to focus on. And so just like with the binomial distribution, there's a formula that we will use to calculate Poisson probabilities. It's maybe a little bit simpler. Let's take a look at it. And so this is what the Poisson probability formula looks like. So there's just a couple of new items in here that you might not have seen before. For one thing, there is a Greek letter here that we may not be familiar with. This is the Greek letter lambda. And we'll use this in the Poisson distribution to represent the average number of events that occur during a given time interval. Like with the customers in the bank, suppose you were told that during a normal day, 10 customers use the ATM during the lunch hour. That would mean that lambda equals 10. Okay, in other words, this is a number that you have to be given in the problem, and it represents the average number of events that occur during that time frame. Now, of course, we already know that this is our factorial operator. This is something that you might not have seen before. E is a constant. It's approximately equal to 2.71828. And it goes on forever, just like pi. In other words, it is an irrational number. The number of digits is infinite and they do not repeat. So you might say, well, why do we need this constant? It turns out to be extremely useful in a lot of applications, especially in finance, where we tend to use it to calculate, for example, how much money we'll have in the bank at a given point in the future. So you do see this from time to time throughout math, statistics, and economics, and finance. There's a button on your calculator somewhere that will calculate this for you. Yeah, there it is. So let's say if you went to your calculator, if you hit second to access this function, e to the x, I have to quickly change this into a superscript. You would hit a second followed by the button that's labeled ln. Okay, so in other words, if you wanted to know, for example, hold on. E is determined as e to the first power as follows. So there's, if you want to remember what E represents, then what you would actually do is go to the calculator and type in e to the first power. But how would you actually do that? Hold on. All right, so on this calculator, what you have to do, let's see, every calculator is different. You would type second ln, and then, whoops, hold on, second ln 1, enter. And this would give you 2 point, as I said, 71828, et cetera, et cetera. Okay, so in other words, if you've forgotten what E equals, this is one way to get it. Just go to your calculator and solve for e to the first power. And the way you do that is hit the second log button, then you hit the 1 and the enter, and you'll get your 2.71828. Now, you're going to need this to calculate Poisson probabilities. If it's a negative number, let's try another example. Let's try e to the negative 2 power. Is calculated as follows. Okay, so we hit second log, and then for this part, there is a negative button in the bottom right-hand corner. On your calculator, it's listed as parentheses negative, and then you would hit 2 to avoid confusing it with the subtraction button. So you'd hit second log negative 2, enter, and your answer would be 0.1353, et cetera, et cetera. Okay, so in other words, you need to be able to calculate e raised to positive exponents as well as e raised to negative exponents, because if you look at this formula again, you'll see that you do in fact have e raised to the negative lambda power. All right, so with that being said, and again, lambda is the average number of events that occur during a given time interval. That has to be given to you in the problem. All right, so let's take a look at a quick example. Suppose that the number of messages that a person receives on his or her cell phone averages 1 per hour. So already you know that lambda equals 1, because that's how this whole problem is defined. What then is the probability of receiving 2 messages in the next hour? Okay, so if normally you get 1, what's the probability of getting 2? Well, lambda equals 1 because we get an average of 1 phone call per hour. X equals 2 in this formula. Okay, the lowercase x, let's see, go grab this one again. That lowercase x is 2. Because we're trying to figure out the probability of getting 2 phone calls. So when you plug in all these numbers, you can see now e to the minus 1 is multiplied by, now lambda is 1, so that's going to be 1 to the second power divided by 2 factorial. So 2 factorial, as you recall, is 2. So just a reminder, 1 squared is simply 1, 2 factorial is 2. Therefore, 1 squared over 2 factorial is simply 1/2. So what you've actually got here is 1/2 of e to the minus 1 power, or approximately 0.18395. So it's a fairly straightforward calculation. But of course, as you can probably guess, the calculator has this function built into it too. So if you wanted to do it with the calculator, this is what you can do. So you go to the second VARS menu, and you would choose Poisson PDF. And by the way, you'll notice if you look at that list carefully, there is a CDF. Don't use it unless you're using cumulative probabilities. So if you scroll down, Poisson PDF is number, on mine it's C. Okay, and once you get to that point, what it's going to do is ask you for two pieces of information. All right, what could they be? All right, let's find out. It's going to ask you for lambda. There it is, which in this case is 1. And the x value is 2. And then, of course, you hit the paste function, 1 for lambda, 2 for x, and it comes up with 0.1839, let's say. So there's a little bit of a rounding difference, but that's the correct value. All right. So you can use this formula, or you can go to your calculator and use Poisson PDF. Okay. Now, I did mention in the previous section that there are formulas for calculating moments for the binomial distribution. The same is true for the Poisson distribution. We have special shortcut formulas to help us calculate the moments. And you can see they're actually even easier than they were for the binomial distribution. So again, this saves you from having to calculate a large number of, let's say, weighted probabilities. Like remember the original formula asked us to calculate for each possible x, the product of that x and the probability. Here we don't have to bother with that. So when we're dealing with the Poisson distribution, the mean is very simply equal to lambda. And interestingly enough, the variance is also equal to lambda, which implies, of course, that the standard deviation is just the square root of lambda. Okay, so you got a very simple set of formulas here for calculating the moments of a Poisson random variable. So in our cell phone example, we were told that the average number of phone calls is 1 per hour. So the expected value, or in this case, the expected number of phone calls is just 1, because that's the value of lambda. Then the variance also is 1. And just by coincidence, of course, because the square root of 1 is just 1, the standard deviation is also 1. So all three of those are very easy to calculate. All right, and then one more detail we want to look at. We want to look at some histograms that help us understand how this Poisson distribution looks. We're going to have 3 different graphs for the Poisson distribution, and in each case, the one thing that will be different is the value of lambda. Okay, so we'll have 1, 2, and 5. So here's 1. If you notice, interestingly enough, these first 2 have the same probability. Okay, you do see that fairly regularly with the Poisson distribution, but then the values fall off very, very quickly, just like with the binomial distribution. How about lambda equals 2? Again, you see these 2 have the same probability. Then we sort of have the same falling off pattern, but it occurs a little bit further to the right. And then when lambda equals 5, we have something that's much more symmetrical. And again, we have these 2 values with the same probabilities, but there's a more even distribution on either side of these 2 than you got with lambda equals 2 and 1. So again, you can see these graphs represent, in a way, they're almost like fingerprints. They show you the unique characteristics of each distribution. Okay, so here with the Poisson distribution, we have an infinite number of possibilities, each one uniquely characterized by the value of lambda. All right, So that is it for chapter 6. So now remember, what do you need to do? I will be posting the solutions that we did today on Moodle, as well as the actual midterm. So the chapter 3 and 5 problem sets are due tonight. The midterm isn't due until the 11th, but in the meantime, just keep in mind, we're also going to have problem sets for 6 and 7. So we'll still be pretty busy. All right. So in the meantime, today is Thursday, so we won't meet again until Monday. And when we do, we'll pick it up with chapter 7, which is our introduction to the normal distribution, one of the most important in all of statistics. And then we'll just take it from there. And I just want to also mention that the second midterm is based on chapters 6, 7, and 8. So we won't have to deal with that for a little while. All right. So in the meantime, if there's no questions, I guess we can knock it off a few minutes early today. Happy New Year. Yes, that's right. By the time I see you again, it'll be 2021. All right. Hopefully it'll be a better year than this year. That's for sure. All right. Happy New Year. Yes, you too. Thank you. Happy New Year to everyone. Bye.
Dr. Anderson.
Yes.
Hi. I sent you an email yesterday. I was wondering if you got it.
Oh, yeah. You wanted me to look at your numbers? I'll look at them. It's fine.
Okay. Thank you so much.
Okay. Anyone else?
Just quick, I'm a little neurotic. So I sent you an email with the homework. Did you get it?
Yes, I did. No, you're right. I normally go through and I send a reply to everyone. I just didn't get around to it yet, but I will.
No problem.
But I remember seeing yours. Don't worry.
All right, great. Have a happy New Year.
Okay, you too. Bye. I got to